Alright, so as you probably already have seen the way attendance rate is so low, hopefully it's not because the class is getting unpopular over time, it's because of a spiraling COVID situation, as I mentioned in the email. Alright.你好，30的那个投影机没恢复正常。我刚应该是有重放，现在可能在重放，整个蓝色。好，谢谢。So for those of you who do come, you guys having fun playing with the movement there? Oh yeah. Question the problem with your sign. Better sign.好像还是失效的。那个按键操作无效啊，这个是。对，3点。对。对，它还有开，但是一直都是蓝色荧幕，然后系统没说失效。对，按键操作失效。因为我按了，有点跳错了。好，可以看这它歪掉了，先跳出来看歪掉。好，可以，谢谢。好。Hope you guys are having fun with playing with Pokemon Go data. If you have any questions or problems with your homework, then just email me, because email is the most appropriate way for communication at this moment. And also, as I mentioned in my email, if you you should start thinking about your term paper project. Okay. Because so far I haven't received any email regarding your term paper perspectives. All right, so you just send me a term paper topic that describing your data scores, what you want to study, feasibility, so I can, so your X and Y, what you want to study, and propose finding. It doesn't need to be long, just one short paragraph, and I can evaluate the feasibility of the study and I'll probably give you some comment. Okay. Okay, so for this class, we've got my pointer. We're going to talk about some rather abstruse concept called tree-based model, and also the class model called naive-based. But here's the roadmap here. First, talking about a naive-based model, and talking about the tree-based model, going from a regression tree and then to random forest, which is simply a modification of the regression tree. And talking about the more sophisticated gradient boost machine, pattern machine, GBA. All right, so it was naive-based. So you heard about Bayesian model. It'll talk about The posterior probability is the likelihood function times the prior function. Prior is simply the assumed probability that given to an event occurring, right? So that's usually not conditional on any prior condition. It's based on our belief. So you probably might ask, so what is naive? What's the definition for naive? When we say a person is naive, that means his or her behavior or mentality is very unsophisticated, right? So can unsophisticated be informative, meaning that you tell us lots of information regarding that they can best in terms of explaining variance. That's all we care about in regression model, right? Or the reduction of errors. And to the extent that we can use that to make prediction, accurate prediction. So can a naive model be used for such purposes? So naive Bayes, of course, as based on its namesake, it's a classification model that based on Bayes theorem, talking about prior, posterior likelihood function, right? In this method, you might also recall a term called conjugate prior, but I don't want to talk about it. I have a really irritating derivation process. So they would be under the assumption of independence among predicted, meaning that the event occurring is unconditional on the probability of other event occurring. Okay. So that's simpler because you can simply write a function as a multiplicative product for the probability that y sub 1 occurring for the first observation occurring is unconditional on y sub 2 being 1 on the second observation occurring. Right? So they are unconditional. So if you want to get the joint probability that the two events both occur, you just multiply their probability function together. It means that they're independent of each other. Right? So that's exactly what it said, because naive Bayes method is usually used for classification approach. We have, okay, so some variable, x all the way to xk, they all contribute independently to explaining a class of the event occurring. Right? So that can be used to for like data when you want to do like multi-class sorting or prediction problem. And as we know from the very beginning of this semester, we know that okay, so each and pretty much every variable here we call a feature that we put into a model, they are correlated with each other to somehow. You can say okay, they have low correlation. The pairwise correlation is pretty low between x1 and x2, but while x1 and xk have high correlation. Right? So they are correlated only to some extent. But here we simply adopt the simple assumption that they are unrelated. So that they'll contribute independently to explaining an event occurring. Or simply the probability that the observation should be sorted into one class versus other. While in reality, that's the ugly fact that this variable actually their explanatory power actually depend on each other. So there may be some correlation that we can forward by other variable present in the equation. Or maybe upon the existence of some other feature. And because of this simplicity assumption, so that's why it's called naive. Say, oh, this class model is naive. So, and it's very easy to build since it doesn't rely on this astronomical correlation. And the good thing is, though it's not only easy to build, it's because in many contexts, for example, like high dimensional, and try to do some text mining, which we will actually get to in week 13 and week 14. Trying to get a high dimensional data which each dimension is expanded by, say, a text or a word or a term. And you actually find out that most of them are actually not correlated, not strongly correlated. And this is the instant where naive Bayes can be used with possible utility. And they often outperform highly sophisticated classification method when you need to tackle with the extra amount of correlation. But usually, that's the easier model is actually the best one. So again, it's built on the Bayes theory, so that's why it is. The Bayes theory said the posterior probability that something is of certain class, so C is abbreviation for class, given the variable we put into the model, so simply a collection of X variable with here. It's simply a multiplicative product of the posterior probability of C, the class. So this means that so the proportion of observation belonging to a certain class. So, for example, in the ice cream example we're going to show you, you know that we only have 3 classes of ice cream, 3 types of ice cream, 3 flavors of ice cream, right? So, but the number of people who purchase those ice cream across different flavors, right? But that really gives us lots of information. We know that every class and their frequency distribution, so that we can have this. Okay, the X is just the prior probability of X. So here it means just yes or no question. So we know that, okay, so the choice on like 2 or 3, right, is a yes, no, or neutral. Or not really, we know that because we know the frequency distribution. But here it's a likelihood function that just that's we're at there so far. That means the probability of X given a certain class C. And so in this context means that probability of finding something yes, right, given this class. So how many, say, given the choice of something, how many of the observation actually pick that versus how many of the people who did not choice, who did not opt for that particular choice. So here I used the ice cream example to explain that. So here I have 3 flavor ice cream, where I have 2 choices. You can either choose to divide it by that particular flavor or not. So the base probability for vanilla flavor ice cream is simply calculated as, because here's the quantity of information we want to get. I want to get that, okay, so given this flavor ice cream, how many of people actually purchase, say, vanilla flavor ice cream? So now in order to compute that, we need a prior probability of yes, no, and prior probability of the distribution of vanilla flavor ice cream, because that's the class, any class that we want to estimate. And the likelihood function. So this is very easy to compute. So we simply calculate it. So for all those who did purchase ice cream, how many of them purchased vanilla? So you can simply look at it, this part, the leftmost panel of this table. Right, so we got 2 other number 8. We got 8 people purchase ice cream. 2 of them purchased vanilla. So what's the total frequency of yes? 8 out of the total of 24. What's the total number of ice cream given all choice? 6 out of the total 24. And then you multiply them together, you get a posterior probability of yes given the name. So that's very simple. So naive Bayes use just exactly this method to predict the probability of different classes. So we usually use for a sorting problem. So you want to sort this observation to this class or this to the other class based on various X variables that you put into the model. So it's mostly used in test classification or multi-class sorting prediction problem. So for example, in the future, in week 13 and 14, when we begin to deal with text data, okay, I'm going to show you that real quick. text data. I want to classify, right? So what topic does this particular chunk of text referring to? You said, because, okay, so this probably a news, so simply collecting those news article from a website, or this news portal, say Yahoo or MSNBC. And then we want to make some educated guess about what this particular piece of news article is all about. Say, oh, it's about COVID. COVID situation is spiraling upward. Or, oh, it's about the Russian-Ukraine war, the ongoing Russian-Ukraine war. Okay? So we need to classify into a different type of topic, and that's the way to go. Because it has lots of features, and many of the features are actually uncorrelated with each other. Right? The correlation is very sparse. And that's the way to go. So the good thing, so of course, as with most models, it comes with both pros and cons. So the good thing about naive data is that it often outperforms many complicated methods. So mass training data as needed, and especially well suited for categorical input when you try to do multiple class sorting prediction problem based on frequency distribution. Right? Of course, it still has some disadvantage because independence assumption between class and among different attributes, different variables have not been accounted for. Then that's a bad thing because in reality they are correlated. And another minor, even though it's actually a quite serious problem, is about no observation or zero probability problems. Meaning that class or tie not observed. Say of course. Have you run into those ice cream shops in which they offer this strange flavor? So maybe only 1 or 2% actually purchase that in 10 years time, but they still will continue to offer it. So if you want to do some machine learning problem and you have the clerk to collect those data for you, say give me your sales record for the last 10 years. So you probably offer some. Have you tried those like a pink floss ice cream? Those see, there's a couple of ice cream shops that offer it. So you can ask them. So in the last 10 years, how many people actually purchased this flavor ice cream? Say, oh, maybe 0. But we do have this in one of this flavor, right? So that particular flavor contributes 0 inflation in your estimation, and that's bad because. Because that essentially means 0 probability, right? But in reality, the probability an event occurs should be strictly larger than 0, right? Always have larger than 0 probability of occurring. And if you have too many of this feature, then that's bad. Your model will be really bad. So of course, we can account for it by using a place smoothing parameter. So suppose there's the collection of parameter vector that we put into the model. And then n is the total number of observations. D is the dimension of the model, means that the number of variable feature. The next variable we put into the model. So if many of them are actually 0, then your model will kind of contribute not only no information, but also to drive down your estimate. So how do we do? So we want them to get closer, but not exactly equal, right? For the numerator and denominator. So we can take a little bit with this place smoothing parameter by adjusting the value of it. Right? And if you do not want to do this extra scaling, you simply set it to 0 and reduce to the original scale. But if you want to tweak a little bit, you can just add to it. And our common sense or pretty study can suggest that we can simply set alpha the place smoothing parameter to 1, and that should do. And if you increase that to larger value, it will eventually close to 0.5, close to uniform distribution. But they also carry some, let's say, some bad consequences because, well, uniform distribution means that it's uninformative. Means that an event that the thing happened with 0.5 probability or not happening with 0.5 probability. That means that if you tell someone that, all right, say the probability that I will get infected with COVID is 0.5, or I will not get infected is 0.5, and then that guy will simply walk away because you are not telling me anything. Right? It's just like rolling a dice. So that's fine for it. So I will show you a little research of that in the past about simply using naive Bayes. You actually outperform for text classification, topic classification problem. You actually outperform some of the most sophisticated models. And for a reason that's actually beyond me. I tend to think that, more sophisticated models will probably have a better predicted performance than naive Bayes. So here, there's just some small research in the past. Well, this is not our code, it's written in Python, but anyway, just I'll show you this. All right, so here, what I really want to do here is want to classify this official document, policy announcement. Announcing is usually by some NATO country. Whenever they try to initiate an international armament collaboration project, say the U.S. want to collaborate in the development of a new fighter jet with its ally, and then you made this policy announcement saying that, okay, we are in order to say strengthen our bilateral defense collaboration, or simply our national security, and I want to collaborate with my target state, means that my ally, on this particular project for this list of subsystem. And because it's a friendly nation, or simply we are all NATO members. So actually a policy document contains lots of entity relations. So first one, to what extent are we related? So are you a friendly nation to me, or are we both sharing some common ties, some defense organization? And what type of weapon are we collaborating? And why are we collaborating? Against whom? Right. So I collect those documents, trying to do some topic classification about, and also on the level of collaboration. Right. So I estimate, so this simply deploy some of the text document I created. So you can actually tell, right? So I actually tell you what this text is all about and the form of collaboration. This definitely contains some entity relationships. So you can say, okay, so this one is about Canada, Denmark, Turkey, Israel, and also the data collaboration. So I sort them into different topic and type, and then I parse out those data and reduce those redundant word and remove punctuation, comma, things like that, and then simply do text analysis. So I used a variety of classification model to sort those documents into appropriate topic. And I found out that, well, actually the naive Bayes actually worked the best because it had the highest accuracy score. Against, for example, the support vacuum machine, which we learned last week, it barely achieved something over than 60% accuracy. Or for SGBC classifier, it's even worse. But logistic regression, even though I suppose that should achieve better performance, but it didn't turn out to be so. It's not that good. Okay. Also, with other more dedicated models, they are not good as well. So it turned out that actually naive Bayes classifier is the best. So here, one using this example to show you that, or actually the simpler is sometimes the best. All right, so demonstrate what Laplace smoothing. We're actually play around with that in our code. All right, so I already showed you this, right? And the problem is, well, the circumstances when this is covered, or Laplace smoothing method is covered, is when you have lots of, say, zero entry in data, because that will that should render those particular class to missing data, missing value, and then they would contribute 0 information in your estimation, in your, say, naive base or synthetic base model estimation. That means you have no prior, right? You do not have any prior probability, because then that would be 0, right? Because you have no observation in this particular class of data. And this could carry very serious consequences, for example, in text mining, because some of the terms are really rare. For example, anyone heard of this? Have you guys watched the opera or Broadway shows? Have you heard of Mary Poppins? There's the one word uniquely associated with Mary Poppins. It's supercalifragilisticexpialidocious. Right, this longest English word. But of course, if you read all the text, you probably won't see it anywhere. So that in most circumstances, the occurrence, the frequency is just 0, right? So that would cause some problem in our estimation. So how do we do it? We can simply assign it with some value by checking with the place smoothing, the alpha value. And of course, the degree of smoothing actually increases with the value of the place smoothing. So we prefer to begin with 1. So we have an observation of 100 and 33 with a alpha value of 3, 2 variables are put in here. But here we only need to adjust the alpha value, which is a place smoothing. So that should give us something approximately, say, 0.039. That's slightly better than 0, right? But if you increase that to 100, then that also increased exponentially, right? So almost close to 0.343. If you increase that to 1,000, wow, that's a lot, right? That's close to 0.5. And it's actually quite close to the mean value of a uniform distribution. But what's the negative consequence of the uniform distribution? Meaning that it's uniformity. It's that an event occurred with 50% probability or not occurring with another 50% probability. That's uniformity. So that most existing literature will tell you, let's set alpha to 1. That should enough. You only need to give it some value slightly larger than 0, so that they still have some positive value of occurring. So you can set that as a valid, feasible prior. That's what you would need to get in order to do basic estimation. You only need to have some non-zero prior. Okay? Right. So let's get back to our topic. So we play around again with the Pokemon data, which will also help to straighten your thought on your term paper, then on your thorough assignment. So again, we load the package that we need. And then there's a very important package for called the N71. They pretty much contain all the machine learning algorithms and related precision accuracy metric. And then we load the data and do some pre-processing, which you should be familiar with from last week's lecture and from your assignment as well. And then we remove those unwanted column from it. We temporarily assign the dependent variable to the vector code y, and we convert it, or capture it, even to do some pre-processing because we want to convert it to the interval between 0 and 1. We arrange processing and use the predict function to apply this change on the data to get the new data. So the data is the transformed data. And now we add it back to replace the type variable with the original scale. Then we check that split. Finally, it's actually the easiest part is to put put it into naive-based classifier, which is just written as such, naive-based. So it's very easy. The arrangement actually looks like the LN or GLN function you have been familiar with. So that's our y variable, that's our feature variable. When we add to the feature, we're simplistically say and the data source. And we can actually plot it. But before you do that, I would advise that you type the names or the structure to look at what's inside this naive-based output. Because you actually see that naive, if you actually contain a table element. If you look inside table element, so it contains lots of value. The table element actually includes the predicted outcome. Here we have three types of predicted outcome. We have water type, fire type, right? And grass type. That's our y value. And also the mean value is standard deviation of our predictor. That's the variable included on the right hand side of the equation. For example, we have to predict against fire, against water. Right? So here, what I'm going to subset is that, okay, so I want the table to look at this particular feature against the first outcome, fire. Here, the second curve, I wanted to look at the same feature against the second outcome. And the third curve, I want to look at the first feature. This is exactly the same feature against fire, against its ability to distinguish observation against this outcome, water. And for all three rows, actually, I set the column vector to 1, meaning that I want to extract the mean value. And for the second argument, I set the column vector to 2. That means standard deviation. So if you look into the naive-based classifier, the table element, you're going to see that we'll show you all the predicted outcome. But here we have 3, right? Also the predicted. So you need to subset it. For example, it's the ND, so supposed to, I simply have the algorithm ND, and then subset the table, and then subset again for one of my predictor, say x1. So you will have this, and the 3 rows, because we have 3 outcomes here. And 2 columns. The first column is simply the mean value of x1. The second column is the standard deviation, standard error of x1. So you can do that. But here on the plot, you do a density plot. See how you predict against this outcome. So you can see that actually against fire, its mean value is particularly informative about predicting water type volcano. Right? Because we suppose that they are quite correlated, right? Because against fire probably means that you have is obviously diametrically opposed to feature related to water, right? But for others, they are close to 0. They are quite uniform. You can also play around with other feature frequency against water. You should probably see that because against water, the attribute should probably spike around its mean value, particularly against fire type. You said, well, this is a little bit too complicated. Want something simpler? Then you can use cloud package. And the method that the way that you put those variable into is very simple. But only difference is that okay, you begin with a capital letter. The function begins with a capital letter. Then the rest is just the same. And you do not need to plot this density plot because you only need to use the plot function to wrap around this naive base output, and it will give you this just simple, very simple. It also include a legend. You don't need to call the legend by yourself. Right. Again, so how does the predictability fare? How does the model perform? So when you train the model on the training data, so how does the ability to predict relevant category in the testing data? So we simply do this. So again, we simply play around with against the data in the training data in which the model is built up. So we should see how they are highly correlated, and so the accuracy should be very high. Again, they're actually quite high. So what's its ability to predict testing data for data that it hasn't seen before? So simply put testing here, and then we put the predicted value as the first argument in the table function, and the true value from testing data, true outcome value testing data as the second argument in the table. Okay, so we actually get higher accuracy score than that. Okay, so we can say, well, I remember that last night you said some of the Pokemon actually do not have a clearly distinguishable attribute. So maybe it suffers some missing value problem, right? And that's why the place losing parameter is geared toward 2, right? So we can temporarily set a place loser to 0.5, or if you want, you can keep adjusting this particular value and say 1, because most existing studies suggest that 1 should be enough. But here I just use 0.5. And then we do the same thing. Then we compute the accuracy, which shows that, oh, it's actually the same. That means that, okay, so our data problem did not suffer too much from missing value problem. So we probably do not need to use the place loser. Any problem here before we jump down to tree-based model? Okay. So what is a regression tree? You've all heard that a lot. So what's that different from linear regression model? I haven't learned this so far. All right, so the regression tree compared to linear regression model, which simply will fit the model on food data, that means major global estimation. Global means that apply to the entire environment, simply apply to the entire data. So, for example, when you're wrangling with R and Python, you say, I want to call something or convert something to something, and then simply leave it on the screen. Instead of a subset thing, or simply you enclose that within some programming language. You say, oh, I only fix it or reset it under under a particular console inside R or Python. Then your interpreter, your Python or R interpreter wouldn't come in global. It is not applied to the entire computing environment. But here, we said, okay, so simply we are only working on SIN data. So if we only fit one regression model for data, means that it's a global estimation because it applies to all the data that we are working on. But there are definitely some, say, local regression or localized environment. For example, when we're talking about the Lowy smooth, right? That's the local regression. It only applies to some subset of data. Well, regression tree is somehow similar because regression tree is built on the iterative process known as binary recursive partition. You say, that's a drop-in status. Okay, right. That's a binary recursive partition. That means we usually rendering this into a decision process, which usually there's a yes or no. So there develops some cut point at each node. And after the cut point, we need to make some decision. Meaning that if some value is smaller or larger than that particular cut point value, we should sort that into the corresponding bridge. So here's the partitioning count. Because you essentially partition the data into 2 parts. So you say, okay, now I get what is binary and what is partitioning. So what is recursive? meaning that we keep partitioning data iteratively. So here's the first partitioning, and then second one, we probably fit, probably give the decision of another value. It could be from the same splitting variable or from another important feature, another variable in our data set. And we keep partitioning based on some given criteria. And of course, we can use the machine to help us make this decision to recommend the best partitioning value. And this iterative process puts data into smaller chunk of data as the method moves out each branch. And as such, by doing so, the decision tree is generated, and each decision node in the tree contains a test some specific value of the input variable that you use as a split variable. And usually corresponding to some given value, saying that if some value is larger than that, it should be stored into one branch. If some value is smaller than that, it will be stored into another branch. So you're using partitioning. And the terminal node, meaning that the final node of the tree, it should contain some predicted value. It's usually a binary decision. So people have been using that to make decisions. And by following through this process, you can immediately tell, okay, so the number of observations at this end node, the final decision node, will be smaller than the original data source. Right? Right, so just to make it, I'll use a simple example to illustrate this. So suppose you're a freshman, recall your freshman year, when you first enter this classroom, so now you meet your classmate for the entering class. Right? So the most intuitive classifier is probably that gender, right? Gender. So now you can put a male student here and grab the female student there. And then so now you have your first split. You already divide this entering class into. So that's a 50-50, right? Into half. And then if you want to further sort this entering class into a more homogeneous group, because that's what we want. Those each of those n should be rather homogeneous to each other. Because they could not be fully split. So what will you do? What will be the next most intuitive classifier? Probably height or weight, right? Right. So for guys that's taller than 5'9" or 175 centimeters, okay, you're sorting into one group. For a guy below this height, you're sorting to another group. And then what will be the third most intuitive classifier? The region or high school they came from, right? And then you can follow through in the smaller group until you finally get to the more homogeneous group. Okay, so those are girls from the city of Taipei. They all graduated from those top all-girl university, all-girl high school. Right? And those are boys coming from say Central or South Taiwan, right? Graduated from the same high school. Now we have some smaller chunk of more homogeneous group because we could now follow splitting data. Or follow splitting, give no additional information to help us reduce the sum square error, because that's what we want, right? Because the data is already homogeneous, so it's not possible to further reduce the error, and then we should stop. And that's basically what so people working in decision science or even in the medical rescue team, the EMT, they have been doing. For example, one of my cousin, who is a paramedic working in the greater Chicago area, so that's basically the kind of situation they've been working on, they've been facing every day. So you need to jump into an ambulance to check on the spot, right? You need to hurry up to the scene and then rescue the person, and you're going to check his or her pulse. But it's still alive. If that person is already dead, then you need to be economical with your medical resource, because well, if the person is already died or died for a few days, then you just probably call city morgue or call the police to handle the situation, and then you should probably drive your ambulance to save someone else who's still worth saving, right? So you need to make lots of binary decisions. So it says an emergency, no. Okay, if yes, okay, we send it to ER, emergency room. Well, if not, see if there are primary care physicians around. Yes, then you send that to the person who's in charge of that. If not, then we should take care of that guy, right? So we actually use similar decision process every day, right? We're just like incoming email, right? So is it really from the important person, or is it from a professor that we're in class and almost get to the point of getting failed? So I should definitely respond to his email. Or is it from a rather distant friend? Say, hey, could you lend me money? So no, get out. Right. So we definitely need to be economical with in terms of our resource and time, energy, right? And because the model uses a tree-like decision structure to represent recursive partition, meaning that we're doing it iteratively, recursive, so each of the terminal node or leaf of the tree, they represent the cell that partition, the resulting cell population from the partition, further partition from the full symbol. And it has attached to it a really simple model that applies to a cell. So what's that model? It could be, say, smaller, so each decision node is a node. Smaller than some threshold value, which is called delta, or larger than some threshold value. Right, so for each subpopulation, so if we're responding to each decision node, each n node, it's usually a simple linear regression. So univariate is actually a univariate model because it only contains one cylinder variable attached to this population. So it's a sub-data 2. So just a very simple univariate model attached to it and apply locally, not globally, to this subpopulation. And at each node, decision node, are usually labeled with a question, say, is this value, but they correspond to the y, right? Smaller or equal to some threshold value, delta. So it's usually labeled with a question. And the age, or simply say range, between those nodes are associated with the answer. You say, okay, yes, then you will be sorted into the top range. You say no, then you will be sorted to the lower range. And the order in which, but here's the most important thing, the order in which those variables are examined depend on the answer to the previous question. So in order to get here, just like get here, in order to get here, your answer must satisfy the condition, right? So whether it is smaller to equal to the threshold value, then you will get here. But the order in which the variable are examined, depending on the importance of this particular feature, this particular variable, in terms of the reduction in sum square error. So usually the first split has the most impact on reducing the sum square error, followed by the second splitting variable, and then the third, until false splitting can no longer improve the reduction in sum square error, and then at that point we should stop. So here, it's an illustration by Bryman, already attached that to the leaf. So for example, that L, the big L, will be the leaf of the tree we end that at, right? The end node that we end that at. So one would be the dependent variable you would be familiar with as being the stopping criterion. So all you have to do is simply to compute based on this value to get to see if false splitting can get us larger reduction in terms of sum squared error. So what's the decision criteria? Right, so they usually provide two decision criteria. The first is, okay, so we should start growing the tree. Means that we should start putting those decision out to start further splitting the data. Until further split, given that in some minimal amount of information that can be used to reduce sum squared error. Or, on the other hand, if you were resolving in leaf now, and leaf now, that contain less than 5% total data, meaning that because the categories, the subdata is too small, so it shouldn't be on its own class, it shouldn't have its own class. It should probably merge for a topic that we talk about next week. It will probably be merged with some other subgroup. And then at this point, we should stop. When first, two conditions. For if the decrease in sum squared error smaller than some threshold value, then we should stop. And you can actually include that in your R code or Python code. You can tell the machine, okay, if that's smaller than this value, then you should stop. Or if the resulting node contains less than 5% of it, if it's too small a sum, then it isn't worth having their own category. And because of this, as you know, there's some trade-off here. Usually a trade-off that we need to achieve between the depths in at the level of splitting, right? Because in each splitting we create a level in the tree, right? And as the level increases, so is the complexity of the tree, and we try to optimize predictive performance, right? And to find this balance, people usually use it in like reverse engineering, because they usually grow a very large tree, right? And then pulling back using cross-validation to see if removing those end nodes associated with smaller subset of data doesn't affect the reduction in sum squared error, or only marginally affect sum squared error, meaning that okay, so we can, because simpler is better, so we can keep removing those unnecessary nodes, while still have large reduction in terms of sum squared error. So that's the way that we can use to find optimal subtree. That's the way to reduce overfitting. Otherwise, if you have too many levels, then that's not good. And at each level of the tree, with a common parent, you see here, they have the two branches have a common parent. We can evaluate whether for this splitting, this extra amount splitting actually reduce sum squared error. Well, if not, then we would be better served by simply removing it, right? So the method is called pruning, right? Just like cutting. Right? Actually, for people working in horticulture, that will work this a lot because the extra amount of branch actually kind of suck out the nutrient that you need to grow the tree, and it's not good for the growth of this plant. Right? So they propose this method. So if the optimal subtree is defined, of course, we can do this just like what we've been doing for the past 2 weeks. Just simply set out the parameter, because here we face the optimization problem, right? Subject to some constraint, right? Just like the boundary multiplier kind of things. And we need to penalize actual amount of the total number of terminal node, right? And there are several criteria that you can use as the penalizer. For example, the L1 is absolute value, which should be familiar with from the lesson regression. Well, the L2, you use square, right? To select the most optimal outcome. So if you impose smaller penalty, then the tree tends to grow larger because the penalty is so small, so you can keep growing. So long as the reduction in sum squared error is larger than the amount of penalty, and the tree can still continue to grow. Or if you impose too much penalty, then you will result in a smaller tree. So you can use the criteria to simulate multiple models across a wider range of alpha via cross-validation to find the most optimal parameter So the process is repeated recursively until you no longer reduce the arrow, the sum square arrow, to some significant amount or smaller than the structural value that you set on the model. Okay, so we were to interpret after that, we go back and play around this regression tree exercise in R. Right, so let's resume the lecture. Right, so let's go back to our part page. So we're going to use the HMD, the mortgage, housing mortgage data as our example data. So first, before that, we need to reload our required package, but we need one of those, particularly the R part tree-based model. So now we also describe what each of this package are used for, because particularly for this week, the tree-based model is very messy. So we can take notice. So we load the data and the subset of required column, required variable. And then for reproducibility, we set range C here. So we do train test split and convert the dependent variable that denies the decision variable, either yes or no, to factor class in order to be used in our model. So we simply put it into our part, right? So the alpha function will simply do the tree-based model. I was going to say after ANOVA, because the recursive partitioning is essentially rely on ANOVA, announced as a variance. Okay, so if further splitting have significantly reduced the model error, sum square error, that means it should be significant. That's why we have to use ANOVA. And then we can first examine the output. So usually I wouldn't recommend simply creating output on the screen, because output actually contains lots of things. But here it's recommendable to do that, because you can actually see how the tree is split without even plotting. So take a brief look at it. Say, okay, so the first line gives you the total number of observations, right? And then here, there's the tree output. So we also have the leftmost at the leftmost side of this panel. The number in the bracket tell you the sequence of the node. So the first node, of course, is the root node, right? So all the branches begin with U. You also have the same number of observations as the total as our original data, because it's the first step in which the data hasn't been subset, right? Right. So here corresponds to N, right? And then the third value is the deviance. Is the amount of errors that we try to minimize. Here is the Y value, but here is simply just the mean value of the predicted Y. Predicted outcome value from the sample correspond the number of sample inside this particular node. So you can see how we change over time. Right, so at the second split, you can see that okay, so at the first group, you have the same number of observations. But here, it's subset into two parts. By the decision criteria. And the splitting variable is IRAD, HI-RAD. Then we have HI-RAD smaller than this particular cut point value.
And if you want to verify, you can add this number to this number, and they should equal to the total number of observations. Just want to make sure that I understand what's going on here. And they correspond to different deviant score. You see that the deviant actually reduce, right? It goes from 202 to this number, right? It will reduce. Same with the y gap. And then you split the data again to see if it can be further reduced. So we have observation here, single observation. So it's a smaller chunk. Then the recommended second splitting variable is the LB rate. They correspond to different decision criteria. So the one on the left means that it's for all value smaller than this particular value, 0.8034951. And then the one to the right means that it should be larger than or equal to this value. And of course, since they are being full subsets, so their number of observations attached to it is smaller. So this one only has 1244 number of observations, and this one has 593. Okay. So now we go back to this one. That's 6 and 7. Again, we use the same variable to split the data. So for any value smaller than this value, they'll be sorted to this bar. Any value larger than equal to this particular value, they'll be sorted into the 7th column. Okay. Again, you can also look at the cost complexity parameter table, called the CP table. If you recall previously, we used alpha to represent cost complexity parameter. That's the value we try to optimize. So we say, all right, so how do I read this? It's so complicated, and lots of turn simple. All right, so here you provide a model summary. So there's the variable that we use to construct the model. As you can see, only 2 of the variables that we include in the model are used, right? Other than the dependent variable, we do not. Like 2 of the variables that are not are tree-based model think that are important feature for splitting data, while the rest doesn't think as important in distinguishing the data. Okay. So here are a number of them. See that? Okay. So we have the root null error. So it's the percent of correctly sorted observation at the first null. So the value can actually help us compute, measure a particular performance. But there are 2 of them because they are supplied under the relative error and X error. So what are they? So the first one, real error, the relative error is just the model error. I mean, familiar with receiver's data. Some square receiver is just 1 minus R squared. It's the error is coming from the model that we use to predict the data. So what is X error? Well, it's simply is the name that refers to cross-validation error used in R. So how to compute those 2 relevant statistics? So we can use the root null error times the relative error to get some resubstitution error. That's the error that computed on the training sample. On the other hand, there are other which, according to the menu, is a more objective function to assessing model fit. That's what it's assessing predicted performance. That's generated by multiplying rule out error with the X error you get from the R output, which is just a cross-validation error. While the CP is the cost complexity parameter. So you probably know what we want to get. So the best CP should be associated with smallest error, because that's when it's optimized. And then this output shows the depth of the tree that we trained from the model. And each row in this table definitely represent a different height, different heights of the tree. And more level, of course, if you have say 10, 20 row in this table, then you should by default have lower classification error. But of course, your model will get more complex because you probably employ more variable to subset to split your data. And this comes with the risk of overfitting. And as usual, cross-validation error, even though it should decrease, but you actually tend to increase after you have surpassed the optimal level of cost complexity parameter. And for the R package, actually it's recommended that. So say, okay, so when should we start? You recommend this rule of thumb. You say, we'll simply supply, we'll simply look at the CP value, which is just cost complexity parameter, this CP value. In a row where the relative error plus the standard deviation smaller than the X error, the cross-validation error, then we should take that row as our optimized cost complexity parameter. And this happens here. And at the third split, we can do some simple example. We say, wow, this is too complicated, I want something simpler. So we can use this, the pre-CP, then it will tell you the same thing. Or say, can I somehow visualize this process? Yes. So you tell people how the decision process goes. Then you can use the R part, the building function, R part plot, or simply plot. Simply plot will work. And then your tree-based model object, tree fit one. And your plot, and also tell you the percentage of sample allocated to this n number at each n number. And for this plot, you use the plot CP, not R part plot, which should distinguish from this one. It will tell you the change in the relative error, which is the error generated from the training sample, as number of tree rows. See that it's probably optimized at the second level, because at the average, the relative error actually increased instead of decreased. That's not how we look. You say that, well, is that because we only limit our search within a small number or a smaller level of trees? Can we continue to grow the trees to the fullest extent possible and then put it back? Or simply we just want to look at how the reduction in the sum square error as the tree continues to grow to see how it changes. Simply to grow the tree infinitely. Yes, you can. You can simply use the same code, the argmax, but simply adjust the control function, set CP to 0, cross-validation 0 to 0, meaning that we do not attach any penalty on the sum square error. So the true will continue to grow, right? And the X val means that the number of cross-validation we use on the training set, compare the error on the training set. And then we generate another tree model object, and we can plot it. Okay, so you can probably see that the lowest level probably occur around here. It's already plotted out for you. But I mean, it's kind of hard to explain. So, what does that mean? Is that the optimized alpha curve when we have 19 stream. Or you can say, all right, so why don't we use hyperparameter tuning to let the data tell us when the alpha value occur, when the model is optimized, when you split that optimized value, random value, at the most optimal hyperparameter. So we can set this hyperparameter. So mean split is the minimum number of split, the max depth, so the maximum level of splitting. The X value is as usual the number of cross validation. So now we input this hyperparameter into our control function and then train another model. And now we can look at the CP table. Or alternatively, say I don't want to go through that many value in my hyperparameter tuning. I just want to do hyperparameter tuning within a more refined subset of data. So you can simply generate a hyperparameter grid as a grid function, as a grid, so that we set the sequence. So every each of the hyperparameters, so here we only have two. The minimum number of split and the maximum depth is all the tree. So here we simply tell R that okay, so the one that on the value of minimum split go from 5 to 20. So there's the minimum value, the maximum value with increment of 1. So for each time you will increase by 1. So that we only have 20 minus 5 plus 1 number of round, right? And for maximum level of the tree, go from A to 1. Go from 8 to 50, with increment by 1. Right. So you can actually calculate how many unique combinations that we need to iterate through in a simulation, given this grid value. Then we can use Hankout or calculate it. This 1 times 15 minus 8 plus 1. Then that's the total number of iterations we need to go through to find the optimal value, optimized value. But before that, we need to generate an object. So we first set an empty object tree as a list object, which we can append simulated value from it. And then we ask R to go through each of this unique combination of value from this two hyperparameter. And then we fit it into the tree list, so that the model object generated will be appended to this object, to this object we created before running the model. And then we can check this out. So you can type add and we'll print out all the model that generate from this different combination of hyperparameter. After that, of course, we won't get the value that has smaller sum square error. And cross-validation error. So how can we do that? All right, to do that, of course, we want to generate two mapping functions from our CP table. So here, what I tell us that I'm writing a function where I want you to look for the column on the CP table that has the minimum value for this column, the CP column, cost complexity parameter. And then you would generate an index. Meaning that, okay, so this value is located in which row? Right? You look at this. Trying to think of this programming problem as this. We have rows of data. Okay. The first row is the row. We have different columns. Right? So here I tell R that we should look for this column and the minimum value and search for it and get an index for it. So this return index. And I use this index to find this particular column that has this minimum value, and then return this value. And of course, you're really good with this programming, you can actually run into a single line code much faster. Well, that doesn't necessarily mean it's faster. Right? But here, just for pedagogical purposes, I just want to do this. And then I want to do the same thing, but here I have different target. I want R to look for cross-validation error, small cross-validation error. So again, it's just the same function. Which row has the minimum value for this under this column, and then it return index. I use the index to subset and to locate this minimum value. And what I'm doing now is simply to map this to search function on the tree object, the model output that I generated previously. So they restore the data and find out the model that having the lowest CP cost complexity parameter and cross-validation error. And I have R to return the top 5 model having the lowest cross-validation error and cost complexity parameter. You see that I actually type -5 instead of 5 because I wanted to appear in ascending order rather than descending order. Because descending means that the one appearing on top should be rather large. Here, since we are dealing with the minimization problem, so we want the top model appearing on top to have the smallest value. So you see that, okay, so that's associated with the hyperparameter that has 16 minimum split and 14 maximum depth, 14 level. So we include this optimized value into our model and then do that again, generate accuracy score. It's not particularly high, but for pedagogical purpose, that's English. Now we get to a related topic called backing. It's not as you're trying to put something in the back. It's a bootstrap aggregating, aka called backing. All right, so before I begin, any question with the tree-based model? Okay, let's go back. Let's see that, okay, so for a tree-based model, we haven't trained on one model. Right? We're working on the same data set and feed lots of models to each of the subset of the data so that each subset of the data is associated with one simple model. But as you can tell, it's probably very exhaustive. Right. So there are definitely other ways to reduce model variance instead of doing this iterative approach. So One alternative is to do this aggregation, meaning that we rely on a bunch of model, and then we generate a predicted average value from it, and then average across all the average value, so that this is essentially, say, average out the variability associated with any single model fitted to a particular subset of the data. So that can help to reduce variance, just as you will when doing linear regression model and ORS model, because the output we get is simply the average value, average predicted value. So there's a method called bootstrap aggregating, meaning that we average across multiple trees to reduce the variability of any single model, and that should help reduce overfitting, often the case in tree-based model or in decision tree model, which should thereby improve our predictive performance. And the method actually proceeds in several steps. So first we create total of n bootstrap sample from training data. Then for each bootstrap sample, we train a single unpruned. It's just a simple regression tree. And then we generate estimated, it's just an average value from that bootstrap sample. And then we average across this n bootstrap sample to get average estimate, the average which is the average predicted value for y, a dependent variable. And it's assumed that it should average out all the variability associated with a single model. So the algorithm also has some really nice, which I think is redundant, but some people find it's really nice. Really nice built-in property is that it will automatically do the cross-validation for you, because every time you try a bootstrap sample, it only contains 63, which I find is interesting. Why is not 66, but it's 63? But it's actually the default set. I tried to look online, but I couldn't find a satisfactory answer. So, but anyway, so every time you try the first one, you would randomly select, you would randomly pick 63% of the data. While the remaining data, which shouldn't be the remaining, because it still contains that 3% data can be accounted for. Then leave out about 33% of the data out of the bootstrap sample, which is out of that sample, means that they became the testing, equivalent to testing data, right? Which can be used to estimate the model accuracy. So whenever you randomly select 73 of the sample, then create, so you can kind of do this, say, 10 times, right? So for each time you were randomly select 73% of the data, 60% of the observation from the data. And then the live out side, which the live out data, which you call it all the back data, it can become your testing data. So for the model you generate out of each bootstrap drop that contains 3% of data, the model trained from it will be automatically validated on this other back sample. Meaning that you apply the same model on the remaining 33% of the data to estimate model accuracy. So it's just like simply work as a natural cross-validation process. Think about it. I forget what I put 80%, 20%, but instead it should be 63, 63. Anyway, I don't want to fix this out. So suppose we want to create, say, three bootstrap sample. So for each bootstrap sampling, we were randomly extract 63% of data, which is created by from the data. So create a first sample, and then we generate a prediction out of this subsample. We then generate a second prediction out of the second sample, which contains another 60% random draw, 63% random draw from the original data. And then we do the same thing for the third sample. So we have 3 predicted values out of this 3 bootstrap drop, right? And then we average them out. We get the mean predicted, average predicted value, and the predicted value for the entire sample. So we can make it hard or use the bootstrap aggregating to do that. The bootstrap aggregating code to reduce model variance. So again, we love this definition of BA data, the trend has slowed, and then convert the outcome variable to vector class. So what do? We simply put essentially the same line of code inside backing, right? The bootstrap aggregate backing as the function's name. And you might ask, well, what is COV true? It means that okay, we want the model to include all the back sample. Right? So that's why if you want an OB sample to estimate the test error, you just set the COV true inside the function, and you would do that. And then we take a brief look at the output and backing output. So here comes the decision time. So we say, how many trees do we need to minimize model variance through the cross-validation process? So you can actually set this in your control parameter. So say, okay, so I want to evaluate this across multiple trees. So we can do that. Okay, so we generate this parameters in the tree that want to evaluate this begin from 10 trees to up to 50 trees. And then we create an empty vector to store our model output, just like what we do with the first one, we name as tree. We create a list object or a list vector. So far they are empty vector because we wanted to, in the future, we want to append an estimated value under this empty vector. And we also tell R that, okay, so the class of this vector should be numeric, and the length, it will become a column, but we need to decide the row, the number of rows, and under that column should be equal to the number of the tree that we try to cross-validate through. So tell R for each sequence of the tree, which equal to 50 minus 10 plus 1, do the following. So simply you would run this bootstrap aggregating model and generate a prediction error. And generate a prediction which we appended, which we first set, that would be included. The error would be included under the error element inside the model output, which we then appended to the ICE feedback. And we can actually plot this out. You see that, okay, so around like 25 to 28 trees, if they use 25 to 28 trees, the rooming square began to decline. It's about the right number of trees. Of course, you can use a more sophisticated method by setting the control function. So we'll say, I want to do 10 times cross-validation to find out. And then you can use the Johnston's trend function. That will essentially do the same thing. But you need to include that in the trend function and change the method to tree back as equivalent to bootstrap aggregate. And then insert the control function just generated the trend control. Also set importance to true, so you would rank those factors as an important feature. And then you check out the model output, and then check out well, because we set importance to true, so you will actually supply a rank of the important factor in your tree model. So we can plot it out. So we plot, we actually enclose the model output, the bootstrap aggregate model output inside the variable encoding. So we can plot this out. See, I actually ring the encodings of those variables, which we use as a predictor. We see that the most important variable is going to be RAM, as we previously, it's exactly the same. Well, the actually get the same result as same ranking in terms of ranking as we just did in our previous tree-based model. And you can also cast it and generate prediction accuracy. So we actually have much higher prediction accuracy than what we previously get in the tree-based model. Any questions so far? No. Now we get to random forest. Well, you know that. Okay, so from bootstrap aggregate, sometimes, okay, so for each model, for each bootstrap drop, even though it's generated from bootstrap resample. So that should properly simpling out those correlations. But instead, the previous study had found that each of the bootstrap random samples are actually still correlated with other bootstrap samples. So what do we do? Okay, so this alternative method to this recommended method is simply to increase the randomization in terms of feature selection, feature selected for splitting the data, and also for sampling the observation. So you call it random forest. So it's typically very few names because previously you said. Previously we used tree to refer to the model. And if you read some of the papers, you tend to use tree to refer to the models. And we train the trees. So what is that? I'm not working in the agriculture department doing statistics. It means model. So you create a multiple model, and each of the model is named as tree. Right? So you have model 1 is tree 1. 2, tree 2. So you create a bunch of models that do that in bootstrap random sample. So random forest means that we are randomly select observation, a random sample observation, and select feature from this lots of tree because the combination of lots of tree is make them into a forest, right? So we call it random forest. So it's usually seen as a modification of bootstrap aggregate that build a collection of a tree-based model that decorrelated through bootstrap resample. Then resample not only on the observation, but also on feature. So it actually contains two parts. The bootstrap part means that each tree is grown to a bootstrap random sample of similar size. So for each time, you simply extract a given number of random sample of similar size from the underlying population or data. And then feature selection, I think is probably one of the most important parts. Random selection. So okay, so I already random select the sample, right? The observation from my data. So what else do I need to do here? Is that one of the property that they bootstrap aggregating sample correlated with each other because they use the same set of features, or the same set of variable as their predictor. So it could be time consuming when the number of variables including the model is large. So I include 50 variables as my predictor. And they are correlated because you include the same number of, the same set of variables to predict the same thing. So even if you keep shuffling on the underlying population, it will probably still get very close results, so they are correlated. So here, it says, okay, so I can narrow down my search. So if you have 15 samples, I say, okay, great. If you have 15 features, and I have 15 variables, so when you're working on a large data set, I say, okay, that's fine. But for each sample, each reinforced bootstrap sample, I will narrow down my search for, say, 10 variables out of the total of 50. And this 10 variables are randomly drawn from this 50 variable. So maybe for the first reinforced bootstrap sample. So I assume you use highlight to represent this is my first sample. Second sample. Third sample. We're going to do it in a very simple way. So suppose I have 10 features, total 10 features. My data set had 10 features. Means I have 10 x variable plus one variable, but 11 column, right? So for each round, I will randomly select 3 features out of it, and the 3 may not be the same. The 3 features may not be the same in each reinforced sample. So suppose for the first one, I only include like the first variable, second variable, the third variable. The second reinforced bootstrap sample will include second variable, seventh variable, eighth variable, for third variable, for third reinforced bootstrap sample will include the fourth variable, fifth variable, sixth variable. So you can see that actually increase the variability, right? But also help you to pick out other dimensions of variance in the data. So if you work on large data and then you keep varying on the different combination of features used to predict the same Y value, and say if you have like a thousand different combinations of this predicting, then you should probably pick out lots of variation here, and there. And then if you average it across this predicted value, you should probably get a very informative prediction. That's its basic assumption. And also, you will be much faster, depending on how you set up those values. Right. So that I do not need to use up all 10 features. On 10 variable in my data set, I only randomly pick, say, 3 or 4 out of them. Right. But through this randomization, it helps to pick out variation here, and there. And that should make a more informative prediction. The same, we're predicting the same even variable. So here's the major differences between reinforced and on the tree-based model. So in reinforced, only a subset of features select at random on the total feature. The best feature from the data set used to split each node in a tree. Unlike vacuum, where bootstrap aggregating, where all features are used, say the 10 features, so that should require lots of computation. But here, of course, it also requires lots of computation, but you'll be faster in any single round because only select the random subset of the 10 features. So you can say only select 3 or 4. So only that's awesome. So you can see they fare better than bootstrap aggregating. So now I'll get to reinforced. So we need the reinforced package, and on this other package, plus the ranger is a really handy function for scoping the terrain and everything. Pick out those variants. So if you're going to use the same data, you're going to compare the performance and doing first doing trend path split. Then you the name of the function is just reinforced. So we do the same thing, just regress deny on the rest of the variable that we use as the predictor, data on trend. working on training data, we can first examine the reinforced model of it. See, how does that fare to the OOB sample and we predict the outcome, which is just the average of the predicted outcome in other words from that data. You say, so how do I read through this? What does that mean? Okay, so for each tree model that you train on it, which is equivalent to the row of this output, because you need to check out what element you have inside this random forest model that you should look at the error rate element. Then you will have the 3 column corresponding to each of the tree model you generate from it. So each of the tree model will give you a classification of the leftover data, all the backs, and that's the remaining data that you use for validating the training set. Meaning that the tree will actually go for the class inside this testing data, the OOB data. So the forest model, the reinforced model, will choose the classification that garnered the most vote as the predicted outcome. And then the vote will be either yes or no. So that's the reinforced score that is assigned to the model. And the proportion of yes is the predicted probability of the outcome in the remaining other back sample. So again, we can also compute the tree that has the lowest OOB error. So this can be easily achieved by subsetting and apply the which mean function theory to the index of the number of tree here. That tree model that has the lowest OOB error. You can also create a mean square error. So here, we want to assemble what the stuff that we have there so far, and then do an exercise. First, optimizing. First, estimating the model and trying to find out optimized hyperparameter, and then re-estimate the model again using those optimized hyperparameter. So again, we use different data. We use NE housing data. So here, I want to look at the data that contain continuous outcome. So we need to, but this is a little different because we need to supply the formula. So this one requires cell price, there's a continuous outcome. All the variable that we have inside the model specify the source of the data. So we first look at the object, and then we use this to find out the number of tree associated with the lowest mean square error. Right, so it's 139. We will calculate a mean square error. So based on that, we want to do hyperparameter tuning across the random data. So I need to specify my hyperparameter, which we can then further optimize. So here, the entry track is the number of tree. And try started is the number of features I want to include in the model. So for each time you will only randomly select 5 features from total number of variables. The stat factor is just a basic setting. At each iteration, the end try number of features will be inflated by this value. We can just use the default value. And in crew, we can really talk about this half an hour ago, meaning that in order to move to the next step, the reduction in the sum square error, or simply here we use OOB error, and we introduce it in the force model, must be larger than this amount, otherwise you should stop. Model should stop. So we can say that as the more conservative value, say 0.001, or you just don't want to waste that much time, and then you can say 1 or 0.1. But 1's a little bit too much. Okay, so you want to hide the real-time progress, you can just type trace to phone so that you will not just populate your screen. And this or this will just meaningless. Also, you can calculate the time needed for implementing this. Because previously we have used the render function. You can check which one is faster. So first I used the render force model. You can do the same thing with render, the render function. See, okay, the second one is actually much faster. Okay, so now we kind of get a sense of how this model is. We want to do hyperparameter tuning with even more refined, smaller vector space here. Simply kind of narrow it down the number of different, the number of unique values that we need to go through for hyperparameter tuning. So we generate as a Greek object. So you can check out how many number of unique combination of hyperparameters that we need to tune through. Okay, there's a total, of 64. So we specify the row, right? The row, and then we iterate them over the number of row of this hyperparameter group. And then we generate a model output on the hyperparameter. Because previously we know that the render is much faster, so we use render instead of using the force. We generate a model output each time for this hyperparameter tuning, and then we append the output under a new column, which we name as O beyond SE. And then we can show the model generated from a unique combination of hyperparameters that have the smallest out of that root square error, and that's the one we are looking for. Okay, so we ranked it, the top 10 model, in the first one. So that's the model that generated with number of features that do number of tree and null size, the minimum number of observation is within a null. And the simple proportion means that the proportion is simple that in each bootstrap drop. So that would be optimized hyperparameter that you want to put into the model. So we include this hyperparameter, this optimized hyperparameter in another estimation, and then generate the output. And also you can visualize once again about how each of the variables contribute to minimize the sum square error. So we can use ggplot2 to help us do that. But before that, we need to we can actually create a data frame that would be easier to facilitate our visualization test. So first I want the graph to visualize it, but to identify the variable. So produce my data. So I subtract the dependent variable from my data, which is in the first column, so -1. I generate a data frame whose first column is the total variable name. And then the second column is the important. The important simply subtract from the value we just generated before. And subset the variable importance element, so you will rank it automatically. So I generate data frame that can include the variable name, also this importance. Contributing means in terms of what we contribute to reduce all of that simple errors. And then if I plot it by reordering the variable, here they will identify the variable in terms of its importance. While the y-axis is just the importance, we need to quantify the scale. And then also color them, separate color to white. the most important variable, as we saw previously estimate, is LD graph, followed by HI graph, the other two variables. So always another thing to look at is the auto plots, the algorithm. Sometimes you can, because you might want to know, so how does this automatic cross-validation process generate through the building property of this tree-based or reinforced model? Better than we first split the data, we intentionally split the data and use the trend model to test and testing data. So here is an exercise. So I first split the data into two parts. I use the building analysis function and assessment is output. And then I apply on random forest same formula, and then I subtract all B, which is just is square root of this MSE mean square average and all B and all B, and then I compare the output with the test error. Means that the error generated from my trend model and testing data. Okay, we actually have the same contour, so it's slightly larger, slightly higher than the test error. Meaning that okay, the building property of the reinforced or tree-based model, the all B data is actually very convenient for comparing the test error. To kind of give you a really intuitive sense about how this model works, and without doing trend test split. So that's our last subject. Gradient descent. It's a gradient boost machine, GBM. So it's if you like to play those say Kaggle tournament, like the student from CS department, you're probably familiar with gradient boost machine. So it's a award-winning algorithm means that you have used that to win lots of data wrangling tournament. They help you to find out important feature, minimize square error. But however, unlike random forest, that usually belong to the single classic model, right? You don't have the same feature, and then that would build it recursively. And then, so probably have the same sample size. The gradient boost machine built on a sample relatively shallow means that they actually do not try to minimize the error at each step. They actually try to minimize error from sequentially by first building a really shallow. So here, shallow means the model probably only have projects that have single or maybe less than 3 level. You have to do not split the data into a really sophisticated, into a really complicated tree. You only have that at 1 or 2 level. These have shallow model. So that the explanatory power of a single model is very low. But it doesn't care about this because if you build out in simple, relatively shallow and weak successive tree, it means that each tree only contributes minimal information in minimizing the substrate error. With the ultimate goal of having each weak model learning and improving on the error from the previous estimation, so that it can connect them together eventually to reduce the total sum square error. So, because of this, there are two main components of the gradient boost machine. The first is boosting. Means that so you're probably familiar with this term when say your computer is down and then you need to reinstall something. You say it's boosting. Right? So that after each iteration, so the first trend, the shallow model, a really weak tree model. So after this run, the model should run again with respect to the remaining error from previous estimation. So that's a boost. You need to run again. Boost the model again to minimize the remaining error. So it's a framework. So to interpret that more formally, it's a framework to improve previous weekly learn model by adding a new, again, another weekly learn base model to the simple sequential. So you can kind of connect several weekly learn shadow model together. So after each iteration, a new model again is created and used to model the remaining error from the previous sample of lots of weekly learn model. This is always the expectation that the error should eventually goes down. Now this gradient descent as far as it can come from. So the purpose of this process is to find some optimal solution, meaning that we aim for the largest decrease in error, even though we did not aim to do this in single step. We're trying to do that in several steps sequentially. So within the local gradient, using a given set of parameters, and as stated. So this process is repeated in each round. With the model moving in the direction of a decreasing gradient until eventually reach the minimum, where we have the smallest sum square error. That's our goal. So it's not like this. So you're giving the data, right? So if you're the first model, the model doesn't need to be a model with extremely strong explanatory power. So it's usually shallow, only contain like one or two predictors. Okay. So after this round, okay, so we explain this proportion time that use yellow to mark that. This proportion of data which is good, but it still leaves you this amount of error, right? So now you need to connect that with the second model, right? So what does this model do? It tries to minimize the remaining error from previous iteration. So that this means that the model boosts again, right? So the boost. And then you see that after this round, the amount of variance that you explain increased, while the error, the remaining error decreased. So that you fit the third model, again, this is another boost. And then you repeat that again and again, once again, until the process is increasing, moving in the direction of decreasing gradient until you hit the minimum, and then we're supposed to reach the lowest sum square, and that's our goal. So it doesn't aim to minimize the sum square error in just single round. You actually try to achieve that in each successive round. So the sequential model with a weak model to only slightly improve the remaining error from previous iteration. And because of that, because only a small incremental improvement in terms of error reduction is made in each iteration, so that one can actually detect to stop the learning process so long as overfitting has been detected, while the accuracy in terms of reduction of error gradually improves. So you can think of this. So suppose in the first run, fit the model, right? So it should represent the function. And then this should leave us with some remaining error. And then we fit the second model with respect to the remaining error. Then we connect this to the first model. And then after that, we fit our third model with respect to the remaining error left from the second model. And we continue this process until the output reaches some predefined function and the model tells us to stop. So the process summarizes where the B is just the total number of the successive model that you include in the model, in your gradient boost machine. So you can visualize something like this. So at each sequential tree is added to an algorithm. So each model, each weekly learn model, is added to an algorithm. So the distance between the true and predicted line should decrease. I say should decrease because you might actually get a round model or a very, very bad predictor, and actually the distance might actually increase depending on if you made a correct guess using the right predictor. So through the improvement in the prediction accuracy, you might might not be as large as initial because it's not what the model tries to achieve singular, right? As you're trying to minimize some square error in each successive run. So it's an incentive. So toward the very end of the process, the predicted value should nearly convert to the true underlying function. That's the core of this model. Now we wrap up with gradient descent. So the process ideally should move the model toward the decreasing gradient. So why should the gradient decrease? Why should it be increased? Well, because we are looking for the minimum. And there are a bunch of studies that suggest that the most important thing is about using gradient boost machines about setting the correct initial value, or simply the learning rate. So what does that mean? Well, because the length of the steps, each step you move along this gradient space is determined by the learning rate. And that's very important because if the learning rate is too small, meaning I only move this step, like almost baby step, then it might take many time or many iterations for you to eventually achieve the minimum. Right? Does that make sense? On the other hand, if you set your learning rate too high, you may actually jump across a global minimum. And after several iterations, your machine will tell you, I couldn't find the minimum. Well, it's not because the minimum doesn't exist, it's because you kind of jump across it without even noticing. And that's why some scholars have suggested, you should keep trying a different initial value. So if you set your initial value here, then just set your learning rate to some small value, and maybe just in one run you actually hit the spot, find the minimum. On the other hand, you set your learning rate too high, you might continue to jump across the global minimum and never being able to achieve the global minimum. So you might end up actually farther away from where you started and never being able to find the minimum despite the fact that the minimum actually exists. So I would say gradient boost machine or the gradient descent is actually an art rather than a science. Right? So finally, the verdict. So it's very flexible, you optimize on different loss functions and provide several hyperparameter tuning in a way similar to what we had done before. But also no pre-processing missing data imputation are needed. But the bad thing is we actually require more trees and we need to connect several models together to eventually achieve the global minimum. And also, so not only is that time consuming, but I think the most important thing is that, especially from the standpoint of us, social scientists, that the result is really hard to explain. So I mean, because in the future you might say we can in academia or simply write a paper with some people with CS background, so you'll be able to deal with the same data with really scientific fashion, so you're using a gradient boost machine. How to minimize the data to achieve a really fancy outcome. There was a plot out the gradient descent process and then submit it to a social science journal, and then the reviewers that don't understand what we're talking about. It's not entirely interpretable. I don't know any of this data or whatever you want to call it. So I cannot review this paper. So that's the bad thing because it's not easily interpretable. But for people located in the sales department, they don't really care about that. So long as they help minimize the data, find out a great solution, right, and that would be. So let's go back and finish out the rest of our exercise. So let's go to the final part of our project, GBA. So we again load all the required packages, play around with my favorite data, secret independence data, train path split. So we also set out a hyperparameter. We want to try 10,000 number of tree, see at which number of tree does the gradient boost machine give us the optimized outcome. as I said, the tree depth just set it to 1. The learning rate, so 1 moving bin is that really small, say 0.001. And 5-fold cross validation, and we cannot set any specify any number of core that we're going to use in our machine. So this will use all the core in your machine. And we do not want R to print out each set of iteration. So that's going to populate our screen. So we do not see that to say false. We will not display it along on the screen. So again, you should return it with the model output GBN fit. So again, as usual, you should check out what's inside this model output. So you can type NAND and see that. Okay, so there's a CV error, it's a cross-validation error. So we subset this element from the model output again. But we're supposed to apply which mean function to get the index of the model that has the minimum RMSE. So we get it, and then we take a square root of it. We'll call this out. And if you do not want to use a specific function, again, you can turn to the Coonan-Jones's trim function. But before that, you need to specify the control parameter. Again, say we want to use 10-fold cross-validation, repeat the CV 10 times, and then we apply it. But be sure to specify your method of GBN so that we use GBN. With the same number of variable, we pass true, and then we generate model output. And we can also try hyperparameter tuning within a refined space, using just only a few variables, iterate only just a few variables. So we said the learning rate, which is a shrinkage, represented by shrinkage, the interaction depth is the tree depth, and the minimum observation in a single node. Say, or if follow splitting only contain, say, this is less than 5% of the data, then we should stop, right? The proportion of resampling from each bootstrap resample. So we set the default to 0.65%, that is 65% of the sample will be sampled, up to 0.88%. Of the number of trees, we do not set it, we simply let the tree grows. Minimum MSE, we do not specify anything. And then we generate index for that. For this part, just simply generate index. And then we write a function to have R to do research over this combination of hyperparameter and to estimate on the same model. So for each index, because previously you said the hyperparameter grid, right? So this would so hyperparameter, you see that as a grid. So each row will contain a unique combination of hyperparameter. So this because the hyperparameter, the first one, H1, H2, you can say it's a minimum number of observation in a single tree node, or the number of split, or say the maximum number of tree in a single, and some other parameters. So each row should contain a unique combination of this hyperparameter. So in order to do research over this different combination, simply go over each row. So that's why the function is this. So we will go over each row in this hyperparameter grid. So we'll simply do this. Then we also create 2 additional columns that we computed from our output that we wanted to show the minimum validation error, cross validation error, also the square root of that. And then we have R to display the top 10 performing model in descending order that have the lowest square error. So, but that's not the important thing because we can simply, okay, so this is the model that contains the top 10, versus the 10 model that have the smallest root square error. But what we really want to look at is to look at the combination of hyperparameter value that led to the smallest root square error. And we simply pick up those optimized hyperparameters and then refit our model again using the hyperparameter here. So we simply include those values and then we can extend the result. And you can also visualize the importance here. So the error is just the direction of your label. Okay, so the CPI is the CPI consumer price index, the most important feature for determining central bank dependence, which is actually very valid because according to the theory, the origins of central bank dependence because they want to create credibility for monetary policy to reduce inflation, and that's exactly true. They rank the importance in terms of the variable importance. And another, if you would now want to use write that many color, you can simply wrap around a summary and you generate this plot for you. And this will probably have time to do that. And also, say, can I use gradient boost machine to work on data binary outcome? Because say, our example is the data set for our example is a continuous outcome. Well, you definitely can. The only thing you want to do here is simply to change the distribution to a polynomial distribution, it's a binary distribution. And that would do. It's very simple. Okay, so it's also this is the same function to do these samples. Okay. All right, so that pretty much wrap up today's lecture. So I would say gradient tree-based model or the more sophisticated gradient boost machine is rarely used, at least in my discipline, because I haven't read that many sort of science journals that use that to tackle this sort of science related data. But of course, people get there are new generation scholars that begin to use that to tackle, to process, for example, like the social media data, text analysis. But for my own research, I still encountered study that employ majority of this data. So I would say it's fine if you decided not to go along with this particular statistical data science. But still, they represent a useful function in terms of augmenting your information from your data and how to also provide alternative ways to reduce model errors. Also, it also looks pretty cool actually. But for me, I would just stay away from this. All right, so any further questions on the third assignment? Okay, so let's cover it today.